Okay, why don't we get started? For the last session today, we're going to start with Olin Shivers here, who's at Georgia Tech, currently visiting at University of Aarhus. And there's the title of his talk, so take it away, Olin.
Thank you. So I should just warn you before I dive into the talk that when we had to pick topics for the talk, I thought, well, don't just give your current talk. For DanFest, you should do something new. And so I selected a talk title for something that I've been wanting to solve, a problem I've been wanting to solve for a while. That was back before Thanksgiving. And then I figured, I'll just go do this, and then I'll give a talk on it. This is probably the last time I'm ever going to do that, because the research was still happening on Tuesday. I started doing the slides when I got on the airplane. I've never done that before, so I have to tell you that this is a snapshot, just to warn you in advance. Okay, so and also before I dive into loops, I want to talk about the Dan effect. So the Dan effect is, Dan was not my PhD advisor. I was not his student, but I'm not sure you could tell the difference. There have been multiple, Dan has sort of adopted me to my eternal gratitude, and there have been multiple points in my life where Dan is just sort of, when I was a little bit lost or adrift, where Dan sort of has parachuted into my life. One time going so far as to visit me in Hong Kong, but frequently, more likely, he would call me up and say, hey, it's Dan, why don't you come to Indiana for a visit? I'd go, yeah, okay, fine. And then I'd get in an airplane and I'd arrive in Indiana, and Dan would say, great, give a talk. So I'd give a talk. And then I think that's what you usually do in your institution. But then Dan would go, great, come in, why don't you, I got my compiler class, come, just talk about garbage collection, because they'll like it. And then he'd lob me into his compiler class. And then he'd just sort of grab me by the wrist and haul me down the hall like this demented ringmaster for a circus. And say, wait, I have this brilliant grad student, and his name is Meyer, or his name is Eric, or his name is Jonathan, and he's working on encryption with lambda calculus, or objects, or some other weird thing, and you got to talk to this guy because he's great. And then I'd find myself in this guy, and then be off to talk to the rest of the crew here, David and Kent and Chris, and it was just unbelievable. It was just an unbelievable intellectual stew. And then you'd go out at night. Dan would then take me out for really bad Chinese food, and we'd. I noticed in the cafeteria today that you walk in the cafeteria and the sign that says, try sushi, fully cooked, naturally delicious. And I thought, welcome to the Midwest. The friendly people is not the only sign that you're here in the Midwest. Sushi, they want you to know, is fully cooked. And we'd sit around at these Chinese restaurants, and then Dan would just lay out the 7-step plan, of which step 4 was world domination, right? And it just, his eyes would start to glow, and it was like the revolution was a party, and you were invited. We needed someone to work on step 2, and by the time you left, you were just totally charged up. So that's the Dan effect, and of course you'd stay at Dan's house, and then we'd stay up late in his office talking about wild ideas. And one night we're talking about some I think it was maybe in-array function call, some hack that we were thinking about. And it's a language, basically doing language design, which is fun to do with Dan. And I'm throwing out an idea, and I say, but I'm not sure what the scope of that would be. What would the scoping principle be? And Dan says, he says, scope is everything. So about every 2 years, some senior academic, somebody who I don't think of as smart, someone who I think of as wise, says the sort of thing that you just think, oh yeah, write that down, engrave that, get a tattoo, and okay, scope is everything. Al Newell once said to me, he said, life in academy means learning to manage uncertainty. And I went, right, write that down. All right, so scope is everything. So that's what leads in, that's why I chose this topic. That was my connection to my occasional visits to Dan. So now to loops, and then we're going to get back to scope. I really, really hate writing loops with tail recursive functions, which is how you do it in Scheme or ML. And I'm going to have to cut short a 20-minute rant on how annoying it is writing loops in tail recursive functions. But I'll just quickly summarize. A tail recursion, as Guy Steele wrote a paper with this title, tail recursion is go-to. like GoTo. I mean, we just don't, is GoTo a good tool to write your loops with? People tend to think that as a bad tool. It's really low level. And also it's not modular. When you write a loop, let's suppose you write a big complicated loop and you're iterating over a list. And maybe you're iterating over a list and maybe also you're incrementing a counter and you're stepping through the elements of a vector. And then I come to you and I say, no, I want to change that first data structure from a list to a vector. Well, you've got pair P tests and cars and coulters and passing arguments. It's scattered all over your loop. And changing it ought to be just changing one line. You want to change iterate over the loop, iterate over the list, like say, just iterate over the vector. Nothing else should change. So the problem with doing co-recursive functions is that information about a piece of what your iteration is doing is scattered. The code is scattered all across the loop. Now, so I would say that tail recursion and Lambda, they make great machine code. That's not something you want to write yourself. Right. And I would also say that map and fold are not the answer. Because map, for example, is going to iterate over a loop. It's going to iterate over a list. And well, what happens if you want to iterate over a vector? Well, you could say, we'll have a map vector. But what happens if you want to iterate over one vector and another vector backwards, and you want to increment a counter at the same time? Well, they don't have that function. Right? And you have to assemble loops out of pieces of iteration structure. Okay? And map and fold are too simple. They don't solve my problem. Now, so then it leads you to the idea of saying we should have a little language, a little form for writing down loops. And this is not a new idea. Okay? Loop forms have been around forever. You have the MIT loop that goes back to Mac Lisp, at least the 80s. That's when I started using it in 1982. But probably goes back to, I mean, is this guy still here?
70s.
Yeah.
70s.
Okay, thank you. Yale loop was done. It was done at Yale, and these are all very similar. The common Lisp doesn't have a loop form; it has the loop facility. It's like the program feature, the prog feature. So you can write programs, right, with prog. I love the loop facility. And then there's the MIT. It's one I think the common Lisp loop facility is a little baroque. There's a nicer one from MIT called Iterate. Anyway, there's just no end to alternatives. I mean, everyone in this room, I'm comfortably sure, has written a loop. And so, I mean, we all have to deal with loops. So people keep drumming up alternatives. Loops are where all the action happens. So there's a nice one that Dick Waters did called OSS or Let S. But it's really striking when you look at Scheme that we have multiple versions for Lisp. You don't see loop packages in use in modern day schemes. And that's a notable, that's something that's notably missing. And believe me, it's not for lack of initial effort. I mean, cue the long 20-minute rant that I don't really have time to get into now, right? Like I said, every time I write a loop, I grumble at how I have to spell all this garbage out and sprinkle it all over my loop and obscure what's really going on. I've been trying to write loop packages for over 10 years. And I always stumble on Dan's line, okay? Scope is everything. What is the scope principle for a loop package? So I've highlighted my principle about how much text you should put on a slide here. But this is just too delicious not to put up. Here's the problem that you get from Common Lisp. This is straight out of the Common Lisp spec. And I'm just going to pull out a couple of significant bits here. It's implementation dependent whether the lexical environment in which the initial value forms are evaluated includes blah or blah. This doesn't say. You ask a question like, hey, what's the scope of this expression? Well, don't know if you write it with the Common Lisp loop package. And then there's commentary, where it has phrases like extremely vague phrases, don't really say much. Let's see, vague statements, unusually large amount of latitude implementations. That's a problem. Now, wait a minute. Now, if you stay out of the danger areas, Common Lisp programmers use the loop package facility, and they get a lot done. All right? I think it makes their lives better. But that's just not acceptable for Scheme. For Scheme, you really do have to have a coherent scope story. And I think that the source of the scope problem is that individual loop clauses, they throw bits of the clause into all over the loop. That's what you were doing when you wrote it out by hand. And so that clause appears in one place when you write the clause down in the loop package. But it's shooting bits of code into all over the loop. And so it's hard to come up with a coherent scope story. So cue Dan, and you got to say, what's your scope story? And I have been iterating over this, no pun intended, for a long time trying to figure out a scope story. So I want to show you the one that I've come up with. Let's see. All right, so let's back up and look at lexical scope. Basic lexical scope from lambda calculus. I would claim that it buys you two things, only one of which is really deep and fundamental. One of which is like handy for humans. The feature that's got handy for humans is that the programmer can choose variable names. When you need a variable name for a loop or a little local piece of code, you can choose a variable name and you don't have to have global knowledge of your whole program. It's not a flat address space. All right, if you need a loop variable, you can use I. And you don't have to worry about whether or not someone 1,000 lines away used I too. All right, so it's not a deep property. What I mean by that is, if I removed that property, it would cost you no computational power. You could write all the programs you used to be able to write. It would just be more painful because you'd have to have global knowledge of your program. But it wouldn't upset a compiler at all. Right? Program transformers, compilers, things that reasoned about programs, they would have no trouble in dealing with a language where if I say lambda x at one point in my program, I can't use x anywhere else as a variable. Okay, it wouldn't be a problem, but it would drive you nuts as a human. Okay, so I would say that that's the shallow property. The deeper property of lexical scope is that definitions control dominate use. And scheme part, that's a compiler terminology. In scheme terminology or lambda calculus terminology, bindings control dominate references. You can't get to a variable reference without going through its binder. You've got lambda x, and here's a reference to x. Control can't get here without going through here. That means when you get to a reference to x, you know it has a value. That is not true in Fortran. It's not true in C. It's not true in SSA. Okay, but it's true in anything that involves lambda calculus. Definitions control dominate use. That's important for humans and computers. So here's the idea. Here's the key idea. Let's take feature 2 as our definition of scope. Okay. So now I don't really intend to spend a lot of time talking about my loop form. It's pretty standard. It's a variant of the Yale design, which is very similar to the MIT/Common Lisp/Lisp Machine Zeta Lisp design, except that it's got a few more parens. It's got some S expression structure. It's all configurable, extensible anyway. It's done with macros. And if you don't like the details of it, you can do your own. Okay? But what I really want to focus on is what's fundamental. And that is the underlying semantics, which is, e.g., scope, and where it comes from. And that is associated with the underlying loop language. And there are two of them. Actually, there's a third. There's something called the loop toolkit, and then there's this language for writing down control flow graphs. And the third one that I hinted at is something called the TCFG, which is a typed control flow graph. And the types here actually talk about scope. Okay. But here's a quick example to show you what the thing looks like. You say, oh yeah, I'm going to have a counter, and I'm going to iterate over a list of students, the variable s. I'm going to increment the student ID from 0 upward, and I'm going to have a vector of courses. I'm going to step C over that elements of that vector. And this is extensible, so you can have for something in a hash table. If you have your own, if you made a doubly linked list package, you could have a little keyword here that would say how to iterate over it. And then you can say, well, every time through the loop, let's check to see if the student has a conflict with the course. If there's a registration conflict, then let's log it using the student ID in the course, and then let's bump the counter. So bind count to count plus 1. And notice that you don't have to have, you don't have to pass along in your tail recursive call 4 parameters by position, remembering which ones are which. Right? You just say, oh yeah, I just want to update this one thing. And then when you're done, the answer is the number of conflicts you found. Okay, that's a loop. So that's the kind of thing, huh?
Is the students being changed also as you go around this loop?
The student?
S.
S, yes.
So how come you have to say the account increases but not the student is bumped?
Because the student, we zip down the student list every time through. I'm only bumping the count when this clause comes out false, you skip the rest of the body. This clause guards the action forms that happen in the rest of the body.
No parentheses around that.
So I assume you could have some kind of iota thing where you would just have a variable that would just increment and wouldn't have to be bound.
Yeah, well that's this one. Actually, that's increment student ID n0. And I could say n0 to 100, and then I'd stop after 100 iterations. But since I just said n0, we're going to start at 0 and count up. Okay, why the colon? If you're wondering, That means we start at 0. If you left a colon out, we start at 1. It'd be it would be a closed, an open interval as opposed to a closed interval. And you can put colons or not colons on the other side to talk about ranges. Small detail, okay? I don't want to get into that. So this is the design of these loop clauses. Now the big picture here is that each of these loop clauses is itself defined by a macro that expands into a set of clauses in this LTK language. And then these multiple different clauses get exploded out into the pieces of the loop, and you assemble your whole loop that way. All right, so Lego blocks and scope. So as I said, a loop clause produces a set of labeled Lego blocks. And these things are then snapped into a fixed iteration skeleton. So a block is a computation. So what do I mean by a Lego block? A Lego block is going to be some computation C that happens in some scope, which we have yet to define. And then you've got multiple edges coming out. And every edge is a label. And these labels can be anything you like, but when you're talking about loop blocks that we're using in the loop macro, they have to be either P, S, or F. P means proceed, S is skip, and F is finish. So you take an F edge, it means I'm done with the loop and I want to go do the wrap-ups code. P means I want to do the next standard thing. And S is when you want to do what in C would be done by continue. You want to blow off the rest of the loop body and go on to the next iteration. Okay? Proceed, skip, and finish. So, and then every edge has to be labeled, has to be associated with some variables. You take this edge, you have the set X and Y. You take that edge, you've got the set Z. And the notion is, this computation, you run it. If control ever gets here, this computation gets to run, and then it gets to choose which exit to take. But if it takes this exit, it has to provide definitions for X and Y, new values. If it takes this exit, it has to provide new definitions for Z. Okay, so an exit edge, E, has a label and a set of loop variables. When the block exits by edge E, you've got to provide values for the associated set of variables. And then now we just apply our scoping principle. Okay, we snap these blocks together into some sort of a graph, and then you say if there's no way to get, if every single path from the start of the program to a given block always contains a definition of a variable, remember, you just look at the edges, then that variable, the block is in the scope of that variable. And it will see the most recent assignment to that definition of that variable. I almost used the word assignment. Remember, we're doing this completely functionally. No assignment, no set bang needed. Okay, that leads me to the CFG language. So there's a little language that you use to define control flow graphs. And it has two binding spaces. It's got a space for loop variables and a space for code labels. So code labels are bound with let star and let rec forms. And you reference them with go. You say go label, and you jump off to the block that thing labels. And these things are lexically scoped with just generic lexical scope. I didn't need anything special here. That's what I used. Loop variables are the kind of thing we're talking about where you've got this weird scoping principle. So they're defined by exit edges. And they're referenced within Lego blocks. So whenever you run one of those computations inside a Lego block, it gets to see the current bindings of all variables that are in its scope. And the scope, and these things are not, these are scoped lexically, these are scoped with this definition dominator scoping principle. So here's the language. It's not very big. So again, the first three forms are really talking about binding Lego blocks, binding code blocks. So let star binds a series of labels. You know, I need a pointer. Do we have a long pointer I could use, or a laser pointer, or? All right, rock and roll. Here we go. All right. This is a label. It's bound to this control flow graph and so forth. And then here's the body. So the idea of this is execute the body even better. Thanks. Because this doesn't show how nervous I am, right? All right. So we execute this control flow graph in the scope of these bindings. And so if you have references like go to a label, then they're always resolved using lexical scope. And this is for building loops, right? This is let rec. Okay, now this is the form that builds a Lego block. So what you have here is a piece of scheme code. And then here you have the various exits. So you have the set of variables and then exit to that CFG. So if you've got 5 exits, you'd have 5 of these clauses. And, okay, here's an example. This is the little Lego block that you get when you decide you want to iterate over a list. So I said for x in some list. So I gen-summed up a temporary variable, loop variable, and I evaluated my list, and I stuck it in a variable called temp. That happened up at the top of the loop. So here's a little block that does the should we continue test. So you say, is the temp, is the current value of the list a pair? And if it isn't, we go off to the finish edge, and there are no variables here because we don't have to. There's nothing to define. If you come this way, we say x gets the car of the temp, and temp gets the cutter of the temp. All right. So these car cutter combinations actually happen in the block, and then those values get pushed out when we go out the edge, and you go off to the next thing you're going to do. You proceed. So how does this look as a little do form? You say, well, I've got two. The thing you write down, the scheme code, is a scheme expression that evaluates to a procedure that takes as many arguments as there are exits. So this Lego block has 2 exits. So we pass this guy exit 1 and exit 2. And it's his job to simply do whatever he wants to do and then recursively call one of these guys when he's done. And if he calls E1, he's got to pass the values for the outgoing values. If he calls E2, E2 takes no values, so it takes no arguments. Okay, so remember that if you look at do, then each one of these exits says, I got some variables, and then here's a CFG. So exit 1 says, I need values for x and temp, and then I'm going to go to p. Remember, so go p, that's a, oops, didn't come out the way a minute. I knew that was going to happen. So that's a CFG form, right? And these are loop variables, and this is scheme code. So I'm mixing multiple kinds of code here. And then here we've got no variables, and then we go to F. Okay, that's a Lego block written out. Now, you can compose what we want is the ability to take these Lego blocks and snap them together. So this is what compiler hackers call a hammock, right? Here's the tip of the hammock, and it's a control branch where you go one way or another way, you do some stuff, and then you join together. Okay, so here we'd say if x is odd, come this way, and here's the definition for y. Otherwise, go this way. Now, when we get here, we definitely, y is in our scope, because you can't get here without coming past here. Okay, so y is definitely defined. So I can say f of y, and I'll get that y. Okay. Whereas if I come this way, then y is not in scope. I mean, let's assume that y was not put in scope by earlier code. So you come down to here, you call g of x, and then we come here and we define y. So no matter how you get to here, you get a definition of y. Right? So this block, this CFG, is going to be dominated by y definitions. So this guy, when you run forward from here, you'll see y. It will be in your scope. And this is how it's written down as a CFG. Okay, here's the top. It's written upside down, basically. Here's the top of the block. It says if x is odd, then go to exit 1, which is here, thus binding y. And that says go to the loop label LA, which is defined up there. Otherwise, we go to LB, which is defined here, and we pass no variables. So A and B are these 2 blocks. So A says, well, okay, call f on y, and then jump to E1, which binds no variables, and that's going to take us to the join point. And this guy is going to say, well, call g on x, and then exit via this edge 1, passing x squared. And that'll get down to y, and then we'll go to the join point. And the join point is whatever we wanted to put. You just write it down. So 2 things to say about this. One is that the dominator tree for this code is expressed by the let structure, the let and the let rec structure. Okay? So if you say, what's the dominator for this guy, this piece of code? It isn't this node, and it isn't this node, it's this node. All right? All 3 of these nodes, they're immediate dominators. By the way, how many of you here know what dominators are? Great. It's this node. So sure enough, they all appear, these 3 guys appear in the scope of that piece of code. We have a let that binds those 3 labels, and then we do the code, and it refers to them. All right, and that's just lexical scope. Okay, the next point is that you can snap together sequences of CFGs using label capture. If I've got 4 CFGs and I want to sequence them, such that when this guy decides to go to label P, we'll go to CFG2. When he decides to go to label P, he'll go to CFG3. and so forth. I just use let star. Okay, so it's do CFG 1, and then when he transfers to label P, what's in his scope? Well, P is bound to that CFG. But that guy, when he goes to P, he'll see this guy. And when this guy goes to label P, he'll see this guy. So I snapped them together. All right, so it's compositional. Right, so now how does the loop form happen? Loop skeleton has 8 major blocks. And every clause expands into a set of CFGs that are all targeted at a skeleton block. So in this fixed loop skeleton is a fixed CFG template. And that's the template, okay? You've got init forms, conditional init forms, a top guard, a body, an update, a bottom guard, so you can do whiles as opposed to while do's. And here's the finish block. And here's the template. And I don't have time, a lot of thought went into, there are various, I'm not going to be able to get into the detail of why this template is the way it is, unfortunately. Right, so let's take this loop clause, for x in append list 1 to list 2. It's going to expand into these two LTK forms. And an LTK form is just a label like init or a top guard. It's which box of that loop skeleton you're going to put it in, and then a CFG. And the free labels of every CFG can only be PS or F. Okay, so it's init says, well, let's evaluate the initial form, append L1, L2, and it'll get bound to temp, and then we'll go proceed. And then every time through the loop, we execute the top guard set to see if it's time to quit the loop. And it says, well, if the temp is still a pair, we can keep going. So pull the head off and the tail, then those get bound to X and temp, and then we proceed. If it's not a pair, then we quit. So 2 things. Intra-clause state. All right, this 4X, this for clause, he's got a private piece of state, which is the list that you're iterating over. It's not exported. It's not visible. Not X. X is an element. I mean the list. That's intra-clause state. It's private. You get that with hygienically gensim loop variables that are shared across these clauses. And then inter-clause data flow is managed by loop variables that appeared in multiple loop clauses. Let's see. I have to skip the type system. Right. What's new? Right. Compiling the CFG to scheme is just a kind of SSA conversion. Well, yeah, everybody, I mean, we all knew that CPS and SSA are similar, and that CPS equals SSA. What's new here is this idea of using definition dominance as a fundamental scope principle, which lets you, and why do we need that? I mean, I'm not saying this is a great general purpose scoping principle. It's what we need for loop forms, because it lets you take multiple components that all have something to do with establishing scope, and you combine them together, and then scope emerges as an ensemble property of the collection. Yet, scope is restricted for the loop form. I mean, you can do arbitrarily weird scoping scope setups when you've got arbitrarily complicated control flow graphs. But we're restricting our control flow graph because this loop form is a skeleton, and you have to slot into it. And that helps you reason about the scope that your clauses create in ways I don't have time to get into. Right. Another idea is the idea of a linguistic. Usually when people talk about SSA, they're talking about graphs. This is a linguistic encoding. So for example, the translation is this incredibly simple recursive type-directed translation. There's nothing about dominator algorithms and the Targe and the Linjauer algorithm, and it's really simple. So it's like, this is almost like a half step between regular code and SSA. So it's an interesting alternate design. And there's this idea of permutable sequences that I don't have time for, and then I didn't have time to get into the type system. But you basically do a type inference step, and that tells you what scoping is. But again, it's not like the usual calculations you do to process SSA. So like I said at the beginning, this is a snapshot. I've done all the analysis, and I've implemented half of it. That's the short summary. And I've been writing drafts of this for years, and I have a lot of examples written. Right, this is quicksort. One of the nice things about it is, something you notice in quicksort is that this is the subloop that steps the left pointer over, and this is the guy that steps the right pointer over. They're not while-do loops, they're do-while loops. You do some stepping and then you quit if some condition becomes true. And so this lets you express that. And what else would I say? Notice that I kind of like the idea that things sort of line up that way. They don't go like river indenting like that. That's a sign that you're in tail recursion help, right, when your code drifts off to the right. Right, here's Knuth Morris Pratt. Here it is in regular scheme, and yeah, you're drifting off. And here it is in a loop form. And another thing that's nice about it is it's very easy to write code that has multiple exits. So here you say, yeah, I want to bind J and CI to some stuff, and then here's a test, and then do some stuff, and then here's another test. If either one of these tests pops the trigger, then you quit. And then when you quit, there's the answer. And so it's more complicated here. The total Knuth Morris Pratt search loop. Hey, can you see there's a nested loop here? Or it jumps right at you, doesn't it? All right. Oh yeah, there's the nested loop. Damn. Everything else lines up. There's the loop. There's the loop. And it's shorter. I'll claim it's simpler. Right. That's all I've got time for. And I'm out of time. But can I take a question?
Any questions? Way at the back.
How does this integrate with the macro system?
Oh, this is done with the macro system. I mean, that's, I use, there's the relevant quote, right? Everything is so easy when you have scheme macros. This is just done with a series of macros. The idea is you write loop, and there's a loop macro that takes all the individual clauses and fires them off. They're all macros. They all fire, expand out into the LTK language, and then another macro picks that up, assembles everything together into one CFG that describes the whole loop. Then there's another macro that takes the CFG and turns it into a typed CFG, an annotated CFG with types in it. And then there's one more macro that takes that and translates it into scheme. It's all done with macros. So, but is that the question you asked? I mean, this works.
I mean,
This.
like right now we have like the syntax rule system or the syntax cases.
Oh, what macro system did I use?
Well, not only that, but how would this play with the syntax rule system, for example? Given
Well,
that the parsing for this system is going bottom up.
It's just. I mean, the loop form is scheme, and it works with a generic macro system in scheme.
The question was those, I think, is do you need to go beyond syntax rules?
No, I mean I'm doing it using something that's less complex and powerful than syntax rule. I'm using just the simple low-level Klinger-Reese explicit renaming macro system. I'm doing this in Scheme 48.
Right.
Okay, and some parts of it I'm actually just doing with R5 RS simple macros. Yeah, there are a lot of macros floating around
Let me
here.
ask the question another way. Is there any computing going on or just shifting around of information?
Heck, there's a lot of computing, right?
Then you're in syntax case.
Then I'm not using syntax case.
No, but I mean metaphorically.
Yes, I'm using a low-level macro package, but I need hygiene to make this right. So specifically what I'm using is the Klinger-Reese explicit rename low-level macro system. But I'm reasonably sure you could do it in syntax case.
Okay, thank you.